In this video, we're going to do a second example problem where we will be able to apply mechanical energy concepts even though there are non-conservative forces acting. You'll recall that if only conservative forces act, we can say that change in potential energy plus change in kinetic energy is equal to zero. However, if we have a problem where non-conservative forces are acting and we'd like to use similar methods, we can say that change in potential energy plus change in kinetic energy is equal to the work done by the non-conservative forces. So here's the problem we're going to do. I have a mass M1, which is attached to a spring, and then the spring connects back to the wall. The spring constant is K. In the initial situation, the spring is at its relaxed length, so it's not stretched and it's not compressed. It's at the relaxed length. Then we have a string that starts at mass 1 and then goes over a pulley and then down to mass 2. Both mass 1 and mass 2 are moving at some initial speed. Now what's going to happen is that mass 1 is going to move to the right, extending the spring, and at the same time, mass 2 is going to go down by the same distance. In the initial situation, mass 1 is attached to the wall by a spring with spring constant K. In the initial situation, the spring is at its relaxed length, so it is not extended and it is not compressed. We have a string that goes from mass 1 over a pulley down to mass 2, and in the initial situation, mass 1 and mass 2 are both moving with an initial speed v initial. Now, what's going to happen is that mass 1 will continue to the right and mass 2 will be moving down. As the masses continue in motion, we're going to have the spring acting on mass 1. That's going to tend to slow mass 1 down. We also have the frictional force between mass 1 and the surface below acting on mass 1. That's going to tend to slow the masses down as well. So when we get to the final situation, both masses have reached a final speed of 0. And also in the final situation, the spring has been extended by an amount x, and also mass 2 has moved downward by an amount x. The numerical values we have to work with are listed here. The initial speed is 3 meters per second. Mass 1 is 5 kilograms. Mass 2 is 7 kilograms. The coefficient of kinetic friction between mass 1 and the surface below is 0.4. And this distance x here, which represents both the extension of the spring and also how far downward mass 2 moved in coming to rest, that distance is given as 0.25 meters. And from this, we want to find the spring constant. We're going to be using this handout that you're familiar with from earlier problems using mechanical energy. Let's just start with step 1. Step 1A, draw diagrams illustrating the initial and final situations. So we have that already. Step 1B is to set the 0 level for gravitational potential energy. Now, first of all, if you look at mass 1 is moving horizontally. And because mass 1 is moving horizontally, we don't really care about its gravitational potential energy. The gravitational potential energy we have to worry about is mass 2. Mass 2 is the one moving vertically. So we have a couple options. One option would be to set the 0 level at the initial position. And the other option is to set the 0 level at the final position. Now, a lot of you might prefer to put the 0 level at the final position, and that's fine. However, I somehow like putting the 0 level at the initial position. So I'm going to go ahead and put in the 0 level here at the initial position. What that means is that mass 2 will start out with a gravitational potential energy of 0 and end up with a negative gravitational potential energy. Okay, so that was step 1. Okay, so we have step 2, option A, if all forces are conservative. Well, we have friction acting between mass 1 and the horizontal surface. That's non-conservative. So let's go to option B. If non-conservative forces act, so what it says is for both initial and final situations, we're going to write out expressions for gravitational potential, spring potential, and kinetic energy. And we're also going to write out an expression for the work done by the non-conservative forces, which in this case is the frictional force between mass 1 and the surface below. So here's what we need. So in the initial situation, we want initial gravitational potential energy, initial spring potential energy, initial kinetic energy. In the final situation, we want final gravitational potential energy, final spring potential energy, final kinetic energy. And we would also like to find an expression for the work done by the frictional force acting on mass 1. So why don't you pause the video here, write out expressions for all 7 of these things as well as you can, and then rejoin the video. So for initial gravitational potential energy, we're going to ignore the gravitational potential energy of mass 1 because it's moving horizontally. So for mass 2, the initial gravitational potential energy is 0 because that's where I put the 0 level. In the initial situation, the spring is at its relaxed length, so the spring potential energy is 0. However, we do have kinetic energy in the initial situation because both masses are moving, so I'm going to add up both of those. We then have 1/2 m1, the initial squared, plus 1/2 m2, the initial squared, and we can combine the terms 1/2 quantity m1 plus m2, the initial squared. In the final situation, mass 2 is below the 0 level, so its gravitational potential energy will be negative. So I'm going to write this as mg, and then for h, I'm going to put in minus x. Final spring potential energy. So in the initial situation, the spring was at its relaxed length, but then mass 1 moved through a distance x, stretching the spring through a distance x. So our final spring potential energy would be, I'll look at the formulas over here, we would use this one, 1/2 kx squared. And in the final situation, the masses are not moving, so the final kinetic energy is 0. Now we have to find the work done by friction as we go from the initial situation to the final situation. To find the work that friction does on mass 1, we're going to do a quick force diagram analysis for mass 1. Okay, so here's mass 1. I guess I'll do the usual thing, put the dashed line. So I'll start in putting the gravitational force. Magnitude m1g. Then going around the dashed line, we have tension pulling to the right. And then from the horizontal surface below, we have the normal force. Now, because the mass is moving to the right, the frictional force acts to the left. And then we have the spring force as well. So we can call that F sub S. Magnitude of the normal force is N. Magnitude of the frictional force would be mu Kn. For the spring force, we could put Fs, but we're not going to really worry about what the spring force is exactly. Okay. Anyway, the mass is going through a displacement to the right. So I'm going to come in and put in the displacement vector here. And maybe a couple squiggles just so we don't confuse it with a force vector. Now back to here to calculate the work done by friction. We can use the usual formula for work. The work done by a force is equal to the magnitude of the force vector times the magnitude of the displacement times the cosine of the angle between the force vector and the displacement vector. Now, if you look at the figure here, friction is acting to the left, the displacement is to the right. So the frictional force vector and the displacement vector are exactly opposite from each other. So we have a 180-degree angle between them. So this becomes cosine of 180. Let's work on this a bit. The magnitude of the kinetic frictional force is mu kn. The magnitude of the displacement, if you look at the figure back here, would be x. Actually, it might be nice to include that in this figure as well. Cosine of 180 is -1. So the only other thing we need here is the magnitude of the normal force. But if you look at the figure here, notice that we have normal force pointing up, gravity pointing down. There are no other forces in the vertical, and there's no motion in the vertical. So what we have here simply is that the normal force and the gravitational force are balancing each other. So the magnitude of the normal force here would just be the weight of the object, m1g. So to get our final expression for work done by friction, I'm going to put mu k, magnitude of the normal force here is m1g, and we have x and then -1. Now we've done step 2 on the handout. Now we go to step 3, and remember in step 3 we have two options. Option A, if all forces are conservative. That doesn't apply here because we have that non-conservative frictional force. So we go to option B, if non-conservative forces act. Non-conservative forces act, we say change in potential energy plus change in kinetic energy equals the work done by non-conservative forces. Okay, so we have change in gravitational potential energy plus change in spring potential energy plus change in kinetic energy equals work done by non-conservative forces. So let's expand out those deltas. Each of these is the final value minus the initial value. Now let's make our substitutions. Initial gravitational potential is 0. Initial spring potential is 0. Final kinetic energy is 0. Let's put in the rest of the expressions. Final gravitational potential energy minus mgx. Final spring potential energy. Oh, I just realized that I forgot to put the m2 subscript here. This is the final gravitational potential energy of m2. Okay, so that should be minus m2gx. Then we have final spring potential energy, 1/2 k x squared, then minus initial kinetic energy from here, equals work done by non-conservative forces, the work done by friction, equals work done by non-conservative forces. So friction is the non-conservative force here, and the work done by friction is minus mu k m1gx. Okay, so that's our equation. So we're trying to solve for the spring constant. So let's just jump into the algebra. So we're going to take these other two terms on the left side and move them to the right. So both of those are going to pick up plus signs. We then have 1/2 kx squared equals, okay, moving this over, m2gx. Moving this over, plus 1/2 m1 plus m2, the initial squared minus mu k m1gx. Now I want to isolate the spring constant, so I'm going to divide both sides by x squared over 2, and I get finally k equals, and this is going to be long, m2gx plus 1/2 m1 plus m2, the initial squared minus mu k m1gx, all of that over 1/2 x squared. Okay, here comes the substitution. As usual, we substitute numerical values along with units. So M2, 7 kilograms, G, 9.8 meters per second squared, X, 0.25 meters, plus 1/2. Now this would be the sum of the masses, which is 12 kilograms. Initial speed, 3 meters per second squared, minus UK, 0.40, and 1, 5 kilograms, G, 9.8 meters per second squared, X, 0.25 meters. All of that divided by 1/2 x. So I'll write the 1/2 is 0.5, and it's x squared actually. So 0.25 meters, quantity squared. When I put all that in my calculator, I get 2,120. Now let's do our unit checking. The unit we would expect for a spring constant is Newton over meter. Now in the numerator here, I see kilograms meters squared over seconds squared. Now let's make sure that the other terms have those same units. So yeah, kilograms meters squared over seconds here, kilograms meters squared over seconds squared here. The denominator is meters squared. Now we want this to come out as newtons per meter. So what we're going to do is cancel one factor of meters in the numerator with one factor of meters in the denominator. Then we have in the numerator kilogram meter per second squared, which is a newton, divided by meters in the denominator. So our answer is 2,120 newtons per meter. And now we have done a second example problem where we used mechanical energy concepts, even though there was a non-conservative force acting.